But then we were looking at various things, various approaches to speed up and slow down rates of neutrophil apoptosis, and that was all going quite well, but we realized that we had some very profound limitations to what we might be able to do. So there are some obvious limitations to the extent to which you can manipulate neutrophils in human beings. So because they only live for a matter of hours, you can't very easily undertake any kind of genetic manipulation of human neutrophils such that you can actually study the outcome of turning on or off individual genes. You also can't observe their behavior in humans under normal circumstances, and we were casting around for a way in which we might be able to do that, and also rather than doing very painstaking experiments, we might be able to do experiments at scale. And this is where we had what was at the time quite an unusual sideways move, because I've already told you that the genes that regulate apoptosis are conserved from very primitive organisms all the way through to man. And the same is actually true for our innate immune response. That ever since we've had vertebrates, we have had granulocytes or neutrophils. So you can go back a long way in the evolutionary tree. And in our case, we went back to the zebrafish, which is one of the most primitive vertebrates, to study neutrophils. And there were many reasons that we chose to do that, not least that fish were very cheap and very easy to manipulate. And unfortunately, I can't show you any of my videos on this SlideShare setup, but we have incredible videos in which we can manipulate the behavior of neutrophils in zebrafish in real time. And the very first experiments we did were we expressed in the zebrafish a GFP, a green fluorescent protein, under the promoter of a gene called myeloperoxidase that in the fish is only expressed in neutrophils. So we were able to make fish that were completely transparent, except that their neutrophils were green. And so we were able to use, these are very early photographs with much more sophisticated live imaging in 3D later on. We were really able to track individual cells. But what this picture shows you is that we were able to take these tiny fish embryos, and they're about 3 millimeters long and about 3 days old. And we were able just to snip the very end of the tail fin. So this is the truncated tail fin. And within 2 hours of cutting that tail, the green neutrophils start to leave the circulation and move to the site of injury. And you see the maximum accumulation of neutrophils at about 8 hours after injury, and then gradually they start to move away again. 24 hours, you can see many of them are headed back into the fish main blood vessel, which is running along here. And you can see that a repair process has already started. So we were very excited by this because it meant we could actually directly image an inflammatory response in a living organism, and that we knew we would be able to modify both the genes that are expressed by those neutrophils, and also you can very cheaply just add drugs or potential drugs to the water in which the fish are swimming and actually start to change the regulation of inflammation. So we were very excited by these opportunities, but also the fact that we could actually start screening potential drugs on a very large scale, or a much larger scale than we could ever have done in human cells. So this photograph shows you our original drug screen, in which we're actually taking a 96 well plate, which you've probably seen, and in the wells we're putting a few embryos. And then, as I say, you can put a different pharmacological modifier into every different well, and you can start to look at the effects of that compound. So we used that to set up a screening assay in which we took the tail fin model, we added various compounds to the water, and then we looked for drugs where they didn't impede the influx of inflammatory neutrophils, because we wanted to preserve a competent host response, for example, to bacteria, but we looked for compounds that then accelerated the resolution of that inflammatory response.